Hey guys, problem number 1 on this pretest. It says in 55 BC, when Caesar invaded Britain, it is rumored he mounted archers on top of elephants. Use the information below to answer the following questions, assuming no air resistance for all these problems. Meaning no friction, right? Okay, part A is just simply to draw the path of the arrow if the archer was shooting horizontally. What I saw as I was looking at a lot of your papers is a lot of people just did a straight line out. Okay, this guy is not shooting a laser for an arrow. It's not going to stay straight the entire time. What I'm looking for in this problem, and for this point, is that you give it that projectile motion curve. So whenever you draw the path of this arrow, it might start out flat, but over time it's going to drop down to the ground due to gravity. So anything with that curve downward is what I'm looking for. Great. Okay. So that's it for part A. That was pretty easy. Part B says draw the horizontal and vertical motion diagrams for the arrow while it's in midair. Okay, motion diagrams. Guys, these are the multiple dots connected with the arrows. I saw a lot of people trying to do graphs, some people doing force diagrams, all sorts of stuff down here. Okay, before we start talking about the horizontal and vertical motion, let's think about what forces act on it midair. It doesn't ask for it, but if I were to do a force diagram, mid-air, the only thing acting on it is the force of gravity. The force of gravity only pulls downward on it. It does not pull left or right at all. Meaning, that force of gravity cannot affect the horizontal motion. Whatever speed he launches this arrow with, it will maintain that speed while it's in the air. Okay, so what that means is, for your horizontal motion diagram, you need to have your axis, straight line down below. We're going to label this 0 on this left side, label it X over here. Starting at a position of 0, so we have a dot. Over time, it'll move to a different position. Remember, the gravity does not affect the horizontal motion. So whatever speed it starts with, it's going to keep that speed. So you should have dots that are evenly spaced for this motion diagram. The last step, all we have to do is connect those dots with arrows. And as you see, the lengths of the arrows will be the same. Great. So now for the vertical motion diagram, we have a vertical line now. Up here we label this 0. We're labeling this Y because it's in the vertical direction. Now, as this drops, its speed will increase due to that force of gravity. Gravity is pulling it downward, so it'll get faster and faster as it drops. So at first, the dots are pretty close together. Over time, they're going to spread out more and more. Then when you connect it with arrows, the arrows will start small and get longer and longer. Okay, those are your motion diagrams. We're not quite done. We have velocity arrows shown. We need to add acceleration arrows. Now, because the horizontal velocity is constant, that means there is no acceleration. So this one over here is done. However, in the vertical, it is getting faster, so we need to include these little acceleration arrows to the side. Mine are just really small. I'm just putting them next to each of those dots, showing that there is acceleration in that downward direction. Great. Great. Part C and D were to make a velocity graph for the horizontal direction and the vertical direction. So draw a qualitative graph for each of those. Remember guys, qualitative means no numbers. I don't need to have a scale at all. Alright, so in the horizontal direction, we just talked about it, it had a constant velocity as it moved to the right. Well, the right is our positive direction. So what we're wanting to show on this graph is a constant velocity on the positive side. So if our 0, undo that. If our 0 is right here in the middle, the positive side would be above this. So it's starting with some positive velocity, and over time, it keeps that velocity. It's just a constant amount. For the vertical direction, we're starting at a speed of 0. Starting off really slow, and over time it's increasing in the negative direction. It's getting faster and faster as it drops. So what we have is a straight line going downward, showing that as time goes on, it's getting faster and faster, further away from that 0 as it drops. Okay, now the calculation problems. So up here in this corner, I have the equations that you'll see on the board test day. Okay? E asks us how long before the arrow hits the ground. So we start by writing what we know. Well, in this problem, they told us that it's being shot horizontally. Here, they gave us that speed. It's being shot horizontally at 55 meters per second. That is only the speed horizontally. Vertically, so our velocity initial in the y direction, we just did it up here. It starts at 0. The acceleration on this problem is due to gravity. So our acceleration is going to be that 9.8 we always use. Second squared. Okay, the height that it's being shot from is that 6 meters that they tell us right there. And because it's dropping that 6 meters, when you write your delta y, you should include a negative sign for that 6. That's all the information we need. From this info, we can find out what the time is. Delta t, that's what we're looking for. To do that, we look at our equations. We notice nothing in this problem has it talked about velocity final yet. And if velocity initial is 0, which it is, we can use this square root equation. Now, I've told a lot of you, guys, this equation is usually your standard equation that you're going to use in order to find time. If you're given a height, and it's usually the acceleration of gravity, you can find time. 2 delta y over a. When you start plugging in your numbers, delta t will equal the square root of 2 times your height, which is that negative 6, divided by the acceleration of that negative 9.8. Make sure you know how to plug that all in the calculator. First, you'll do 2 times negative 6, divided by negative 9.8, and the last thing you'll hit is that square root button. Give me 1 second while I do that myself. Okay, make sure you can get the same answer that I did. If you type it in correctly, you should be getting 1.106. So I'm going to round that to 1.11 seconds. Don't forget your label. That's a point on the test. Our time is measured in seconds. Great. Okay, now for part F, it asks us how far will the arrow travel away from the bow horizontally. So thinking back to this problem, we're still talking about the elephant. He shoots this arrow and it goes a certain distance away from the elephant. We want to know that distance, that delta x. So delta x is our unknown. It's what we're trying to solve for. The horizontal distance away. So if you come to your horizontal equations up here, we have an equation to give us that. Delta x will equal the velocity in the horizontal direction multiplied by the time in the air. Well, our velocity in the horizontal, that's what they gave us over here. They said that he launched this arrow with a speed of 55 meters per second. So our delta x will equal 55 times our amount of time in the air, which we just found right here, 1.11. Once again, you're going to plug that into the calculator. This one's a little easier. So 55 multiplied by 1.11 will give you a distance of 61.05 meters. Your answer to part F.